before I move to the new section, so basically this is the thinking process. So you can see here it still have the same thing here. So maybe you can try to think about if we have the orbit like this, and our target orbit like this. So basically you can see the two orbits, they have misaligned major axis. Okay, so for this case, and of course we can always do the orbit transfer to anywhere. So for this case, you can say pick up, you can design. First one, you need to design your transfer orbit. So for example, you're starting from here. Okay, and then say you pick up, say, intersections of the major axis to here. You simply take the transfer orbit. You can design this way. Or otherwise, if you like, you can say this is my target point here. So say starting from here, then you can design the transfer orbit like this one. So for example, for this case, you can see this is a transfer orbit, and here is tangent, but here is not tangent anymore. So we have kind of the angle, flat path angle we might consider. So that's one scenario. And the other scenario I'm going to talk about is, again, if we have two orbits, so the same thing, so say this is elliptic and this is the target, initial and target. If you like, you can have the transfer to here at any point you like. Again, this is the case similar to this one. So follow-up, we would have the discussions how to take care of this one, that one as the point. Then it's not at tangent. It's not tangent to the target. So how can we do this one? And we will have also the outer plane transfer. So which means if the two initial targets and the initial orbits and target orbits is not at the same plane, they are have the inclination angles. Then how can we do this? So that is the remaining. We probably will go forward. Okay. So probably we'll go to the new sections, and these sections will be onto the a little bit deviated from the orbit transfer, but here that is one facing maneuver. Facing maneuver is to break the rule how to get the things, the two selection objects meet together. So here let me utilize one example to demonstrate the concept, and then you should be able to apply the concept. So for example, here we consider a circular orbit. Once you know the concept, you can apply to any other kind of orbit. And this is the center here. So let me make okay. So at a specific moment in space, we have, say, this is the B. We have two celestial objects in space on the same orbit. Here we consider it a circular orbit, but you can extend the concept to other kinds of elliptic orbits. Okay, and so both are circulating the orbit in the same directions, but A is behind of B by how much? I would say I just give any numbers, 1, 4, 95.7 seconds. Okay, so that is about 25 minutes fall behind. They're on the same orbit. So right now we want to have the things meet together. And again, that is the concept. If you be the pilot, I would say the pilot of the Module A there, if you take the paddle, speed it up, I believe you'll be fired. You'll be fired for sure. Okay. So in this way, how can we do it to make the whole thing? And our target is, our goal is to let A execute, we call the facing maneuver to catch A so let me say this point is point 1, okay, it's a point 1, and where the A locates start to catch B at point 1. So that means I'm expecting when B complete a cycle, get to 1 point here, then A doing the phasing maneuver, then that will meet B at the same time at point 1. Okay, so from here you know this is circular orbit. Let me give you the numbers here. If this is the circular orbit, okay, this can be the circular orbit. Can you allow me to modify the problem statement? Because in my preparation, this is not circular, elliptic. Okay, because here this is the focus, and I have the numbers here. So for here, this one is 6800, and this one is 13600, and units kilometer. Sorry about that one. Okay, so that's the elliptic orbit. So we want to do this way, then the phasing maneuver is this. You can see on the larger orbits, we know the period of making one cycle is always longer than the smaller orbits. And right now, A falling B behind by that much. So hopefully it's this. If B continue to complete a cycle of this elliptic orbit to here, if that would take a certain amount of time, that time must be equal to A. That's going to be on the phasing orbit. And that orbit must have the same time. So A right now is here. So for example, this is the phasing orbit. Okay, so that's the concept. So which means we need to find a phasing orbit that has a period that is equal to from here to here. Okay, so that's the thinking. So how can we do it? I would say if you are the pilot of the spacecraft A, if you take the paddle speed up, I think you are right. You wouldn't be fired because when you speed up, then you'll be docking onto the faster orbit with you. Okay. So the thinking is this. If A on a phasing orbit, which has a period equal to the period of the, let me say, the period of the original orbit and minus this time discrepancies here. And that is 1495.7 and in terms of unit per seconds. Okay, so that is the clue for us to find what should be the appropriate facing angle, the side and not facing angle, facing orbit to complete this mission. So from here we need to know what is this one. The t, we know that one equal to 2 pi and a squared divided by mu, so that is our formula. So for our original orbit, a equal to how much? 1/2. We have the information apogee plus perigee distance, and that one equal to 10200. Okay. So from here we should be able to determine, so this one is 10252 seconds. Okay, so therefore this facing orbit must have the period, that is how much? That is 10252 minus the 1495.7, so that is 8756.3 seconds. Okay, so therefore from this hint, again, we apply the period for the facing orbit. Therefore, we have the time, the period equal to 8756.3. And from there, we can determine the size of the orbit, because that one that we know that t equal to 2 pi A3 divided by mu. So here we can determine the semi-major axis of the facing orbit. Okay, so from here, therefore, the A will be equal to, do I have that numbers being calculated? 9182.1 kilometers. Okay, so here we determined this distance is 2 times 9182.1. Okay, so we have those informations, then we pretty much confident we should be able to do it. And now the remaining is again how much fuel, how much velocity, I would say the thrust vector, the thrust here. So I would say what is the data in here? Okay, at this point, you are the pilot, you need to have the change in velocity such that the A will be onto the facing orbit. And once it comes to here again, then the B will be approaching. To that point, you're going to change the velocity again to move back to his original orbit. So twice. And for each time, they have the same amount of the delta B. And one is, say, for example, increasing, the other one should be decreasing, or vice versa. Are we okay? Okay. So again, so right now for the initial, this is an elliptic orbit, and for our facing, we also is elliptic orbit. So to calculate So for craft A to enter the facing orbit. So right now is, so this is point 1. So that is the, let me use color. So this is the original orbit, and this is the facing orbit. Okay, so I use the color, so that is the facing. This is the original. Okay, the both are elliptic orbit, and we've been calculated, and here is our template. V equal to, we copy from the previous example here, mu over r minus mu over a. Okay, I'm going to base it on this one and apply. So for V, the original orbit at point 1, we can determine its velocity equal to 2 mu divided by r. And what is r? R for original is how much? 6800. And minus mu divided by a. What is a? A is the semi-majors of the original. How much? Let me put into this one a bit better. So again, 2 mu over r minus mu over a. And here I'm going to plug in. So r for the original, that is the apogee distance 6800 kilometers. And a equal to 1/2 of 6800 plus 1360. Okay, so plug in those numbers, then that will be equal to 8.84406 kilometers per second. Okay. For the velocity right now on the facing at point 1, again, 2 mu over r minus mu over a. And for this case, what is r? R, again, at the same point, so they share the common focus. So they have the same r. So r equal to 6800. And what is a? A is the semi-major of the that one. So here we have a being calculated is 9182.1. Okay, so here we calculated that one will be equal to 0.89. Oh. So I'm wrong. So here, let me say this is the speed. This is the speed at point 1 on the original orbit. And let me highlight the magnitude. And this is the speed on the facing. So that speed is a little bit smaller. I'm wrong. So if you speed up, you're going to be fine. You should slow down, but a little bit, right? So that is our calculations. And you apply this one assuming that is a sudden apply, so that means a thrust, and that means you just apply delta V in no time. But usually that shouldn't be happened. It wouldn't be happen. So apply the delta V along a certain period of time. So that means in the real application you need a little bit fine tuning, and that's a more detailed. I just have a few textbook check out from GI. They have a detailed calculation saying they apply the thrust in a certain finite period of time. They haven't kind of refined the formula, but here we're zooming. So from here we can see the delta V, and in terms of the magnitude. So that would be the difference between the two, 8.84406 minus 8.5921. Okay, so when they enter the phase orbit, they must slow down by delta V. Okay, so the slow down by that much, then spacecraft A will get into the phasing orbit, and then hopefully, and they A and B will meet at point 1 once they complete the whole things. And then once they meet there again, so for craft A to back to the original orbit again, so basically another delta V should be applied. So with the same amount, but they're going to increase because he needs to switch from his phasing orbit back to original. So from here, the delta V should be the same because the same calculation you can verify, but this time you need to speed up. Okay. So in total, in this way, the total delta V we're going to have is 2 times so that is the information for the missions control planning. That is a field we can relate it to take it up for this kind of things. And you might have a question is, how do I determine these numbers? Okay, how do I know, say, if this angle, if this spacecraft respect to the focus is certain angle, true anomaly, how do we determine this one? That one will be the topic in chapter 1, 2, 3. Right now we chapter 3. And once we finish chapter 3, we're back to the chapter 2. And then we will continue to chapter 4. This content will be introduced in chapter 4. And that one will allow us to determine the timestamps of the objects on the orbit.